Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.3. The fundamental theorem of calculus and the definite integral.
Lesson 3. The geometry of the definite integral. Part 2.
So let's go ahead and remember what that important question was that we asked just before we did all these properties of definite integrals. Remember, we were wondering, what does this definite integral from a to b of f of x dx represent if f of x isn't always above the x-axis or at worst on the x-axis between a and b, the interval that we're integrating over? Well, first, I want us to think about what happens, what this definite integral represents graphically when my function f of x is less than or equal to 0 on the interval from a to b. And what would that mean about the graph of y equal f of x? If it's less than or equal to 0 on our interval, that means that the black curve lies below the x-axis, or perhaps on the x-axis, but does not go above the x-axis. So we were kind of wondering, well, what does the definite integral represent in that case? We wondered whether perhaps the definite integral represented this red area between the black graph and the x-axis, but we really didn't know. Well, think about it for a moment. If we know that f of x is less than or equal to 0, what could we say about minus f of x? If you simply multiply both sides of this inequality by a -1, on the left you'll get minus f of x. Remember, multiplying an inequality by a negative means I have to switch the direction of the inequality sign. So negative f of x would be greater than or equal to -1 times 0 would still give me 0. So if f of x is less than or equal to 0, minus f of x will be greater than or equal to 0 on the interval we're interested in. So if the graph of y equal f of x lies below the x-axis, notice that the graph of minus f of x, so I wrote down here, here's y equal minus f of x, that graph is actually going to lie above the x-axis. Not only is it going to lie above the x-axis, but it's really a reflection of this picture across the x-axis. So if you thought of folding this paper right along the x-axis upwards, you would end up getting an impression that looks like this. So I want to point out that this area that's under this curve that lies above the x-axis, the curve y equal minus f of x, and I said let's call that area A, would actually be the same positive area that there is between the curve y equal f of x, which lies below the x-axis, and the x-axis. So just notice that this red area up here would be exactly the same as this green area, and I'm calling that an area A. Well, something else we can say. We are now looking at a curve y equals minus f of x that is above the x-axis on our interval. So by the version of the fundamental theorem of calculus that we proved, that means that if I integrate that function, minus f of x, from a to b, I should get the area under that curve. So I should get a as an answer to the integral from a to b of minus f of x dx. That's just the fundamental theorem of calculus applied to a function that we know is above or on the x-axis, but does not go below it. Well, but there's another way to express the integral from a to b of this same thing, minus f of x dx. What I'm going to do is rewrite what's inside the integral. So I'm going to write this as the integral from a to b of minus 1 times f of x dx. I did that to emphasize the fact that we really have, lo and behold, a constant multiple multiplying f of x dx. And remember, we just proved a property, I believe it was property number 3, that said that if I have a constant multiple times f, I can pull that constant outside of the integral symbol. In other words, the integral from a to b of minus 1 times f of x dx is exactly the same as minus 1 times that definite integral, times the integral from a to b of just f of x dx. So I've pulled the constant outside the integral sign, okay, and let me just write this a slightly different way. Instead of minus 1 times whatever number this definite integral comes out to be, I'm going to write it as minus that definite integral. Okay, now I want you to think about the following. I just said the integral from a to b of minus f of x dx is equal to a. But I also said the integral from a to b of minus f of x dx, if you follow this all the way down, is equal to this, minus the integral from a to b of f of x dx. Well, if both of these things that I've circled are equal to the same thing, they must be equal to each other. And that's what I'm going to write down in the next line. This thing that I circled here in red has to be equal to this thing that I circled in red. It has to be equal to a. So I now know that minus the integral from a to b of f of x dx is equal to a, where a is this green area that we had under this curve. What did I want? I wanted to know about the integral from a to b of f of x dx, not minus the integral from a to b of f of x dx. Could I get what I want from this? Sure. All I have to do is multiply this equation through by a negative 1. If I multiply the left side by negative 1, this negative times a negative will become a positive. And if I multiply the right side by negative 1, I'll get minus whatever this area under the curve y equal minus f of x is. So what do we have? Let's write it down in our green box. On this side now I just have the integral from a to b of f of x dx, and on this side I have equals minus a. In other words, it's minus this green area. But remember, at the start of this discussion, when we talked about the relationship between f and minus f, and we said they're reflections of each other, well, this area of this green shaded portion is exactly the same as this positive red shaded area that I have here. So what have we said? We've said that if I have a function f that lies below or on the x-axis from a to b, the definite integral of that function from a to b will not be the total positive area between that curve and the x-axis. It will actually be minus that area. So whatever positive area I would have in here, this definite integral does not represent that area. It represents minus the area. I'll put minus the area between our curve f and the x-axis. And that's true whenever f is below, I should really say below or on the x-axis on the interval from a to b. So that's kind of cool. If this function lies below the x-axis, well, then the definite integral from a to b of f of x doesn't quite represent the area, but it does represent exactly minus the area. All right, well, let's go to the next page. Now, on the next page, I want us to consider our last situation, and that is this question. What does our definite integral from a to b of f of x dx represent graphically if the function is partly above and partly below? In the picture that I've drawn, it's above, it crosses the x-axis at one point, and then it's below. But it could be a function that's above and below and above and below any finite number of times between a and b. So my question is, what does this definite integral represent in that case when it's partly above and partly below the x-axis on the interval from a to b? Well, let's try to fill in this sentence to begin with. Remember that we are still assuming that f is continuous on this interval from a to b. And because f is continuous, if it's going to go from above to below or from below to above, the only way the curve can accomplish that is if it, I put down it must, what must the curve do? it must cross the x-axis. And I'll put down at one or more points. So it may cross just once if it's partly above and partly below. But as I mentioned, you could also have a graph that crosses many times. So it might be above and then below and then above and then below and so on. So it might cross at any number of points between A and B. Well, just for the purposes of this argument, let's assume it crosses just once between A and B, and a similar argument works for any finite number of times that the curve might cross the x-axis between A and B. So I'm going to assume for arguments, for the simplicity of the argument's sake, that it crosses at one point between A and B. And let's call that point something. I'll call that place where it crosses, I'll call that x value the value c. Well, remember that we had another property of definite integrals that we just proved. I believe that was our property number 5. So I'm going to put down here by property number 5 for definite integrals. That was the property that allowed us to split an integral all the way from A to B up into a sum of two integrals, an integral from A to the intermediate point C, and then another integral from C up to B. So remember that the integral all the way from A to B could be split up into the integral from A to our intermediate value C of f of x dx, plus, let me make that C a little darker, plus our integral from, and what should go down here we need to go from the rest of the way from C to B. So I'm going to put from C, our intermediate point, up to B. And we actually proved this property for any function little f. It didn't have to be a function that was always above the x-axis. And we also proved it actually for any point C. It didn't even have to be within the interval from A to B, but in our case it is in that interval. Okay, so that's our property. But now let's think about each of those integrals separately. I'm going to start by thinking about this first integral. In the picture that I've drawn, the integral from A to C of f of x dx, well, notice that the graph is entirely above or on the x-axis on that first interval from A just up to C. And so we know what this integral represents. It represents the positive area between this curve and the x-axis. It's really the area under that curve. I'm going to call this area, this green area, A1. So since this is above the x-axis, or I guess it touches the x-axis at C, but it's above or on the x-axis on the interval from A just to C, this represents that area, A1. Now let's think about the second integral that I have here, the integral from C to B of f of x dx. And what do you notice about the function on this interval? Well, now the function lies entirely below the x-axis on that interval. So remember that in that case, the definite integral, and this is what we just showed on the previous page, this definite integral does not represent this positive area. It actually represents minus whatever the area is between our black curve and the x-axis. This will have some value. Let's call it A2. So this definite integral will be minus that area. So what do we end up saying then? The definite integral all the way from A to B of my function, that's partly above and partly below, is not really equal to this total positive area. It's not A1 plus A2. It's really the area of any portion that's above, and then we add minus the area of any portion that is below the x-axis. So let's summarize inside our green box here That means that this definite integral from a to b of f of x dx doesn't equal the total positive area between our black curve and the x-axis. It isn't a1 plus a2. It's actually a1 minus a2, where a1 corresponds to the portion where f is above the x-axis, and a2 corresponds to the portion where f is below the x-axis. What we often say is that the definite integral in this case represents a difference of areas or another way of saying it is we say that it represents the net area. The area that's above minus the area that's below. Now in our picture, our curve crossed the x-axis at only one point C, but the same thing would be true if it crossed it many times. You would just add up all the areas that are above the x-axis on that interval from A to B, and you'd subtract off all the areas that are below the x-axis. I want us to return to the example that we had a few pages back when we started this whole red starred question, because we had a particular example that we weren't really quite able to interpret the answer that we ended up getting. And now that we've talked about this definite integral for a function that's partly above and partly below the x-axis, we can analyze this example. So we did this quite a few pages ago. We were doing the definite integral from -1 to 2 of x cubed dx. And remember that we said, ooh, well, that's the x cubed function that's going to be partly below the x-axis on this interval. From -1 to 0, it's below, and then from 0 to 2, it's above. And we saw that we got some answer here by just plugging away, finding the antiderivative, plugging in the upper limit, subtracting the value at the lower limit. We got 15/4 as an answer, but we didn't know how to interpret that answer. I said, what does this number represent graphically? And I even asked the question, is it the total positive area between this curve and the x-axis? And now we can answer this question. For example, this one that's in parentheses, is it the total area between the x cubed axis, between the x cubed curve and the x-axis? No, it is not. So no, it's not the total positive area. It's really the difference of areas. So it's the difference of whatever area is above this green area that's right here, which I believe turns out to be this first number in our calculations here. This area right here turns out to be an area of 4. If you just integrate x cubed from 0 to 2, you'll find out that you get an area of 4 for this green area. But this portion in here is going to subtract when we figure out the net area. And this portion ends up having an area of 1/4. So this little red shaded thing right here, the positive area there is equal to 1/4. So what did we end up with? We ended up really with a net area. It was the area that was above the x-axis, that's the 4 that's right here, minus the area that is below the x-axis. That was the 1/4. So this 3 3/4 or 15/4 does not represent the total positive area. It really represents a difference of areas. So I'll just say here, no, it represents a difference of areas. Or some people like to say it represents the net area. Net area. And it's always the amount of area that's above the x-axis on the interval you're looking at, -1 to 2, minus the area that's below the x-axis. Okay, great. Well, let's go ahead and go on now to the next page. What I want us to do next is to think about some specific examples that involve functions that are partly above and partly below the x-axis on the interval of integration. So in this example, it's kind of unusual because it says use geometry formulas to find the definite integral from -3 to 8 of the function f of x dx. Now notice we aren't actually given the equation for f of x. It's just this kind of crazy function that has all these different parts. If we wrote out what the equation for f of x is, it would be a piecewise function that has different portions to it. One portion would be described by, this is a semicircle here, so by the equation of a circle. Other portions would be different equations of lines. But we're not going to worry too much about that because we're not going to do this definite integral by finding an antiderivative of little f. We are asked to do it using geometry formulas. So let's see if we can think about how we could do this problem without actually finding an antiderivative the way we normally do a definite integral. Well, first of all, notice we're integrating from -3 to 8. So I'm starting here at -3 and I'm going to integrate all the way up to the value 8. And I'm also noticing that f of x is partly above and partly below the x-axis on that interval. From -3 up to, it looks like 0, it is above the x-axis. From 0 up to 6, it is below the x-axis. And then from 6 to 8, it is above the x-axis again. Well, remember what the definite integral represents geometrically. In this case, we said that it is a difference of areas. It is the net area. So if we want to find the value of this definite integral, if we could somehow find the values of all these different little areas in here, we could go ahead and say, well, the definite integral from -3 to 8 will be whatever positive areas are above the x-axis minus whatever areas lie below the x-axis. So the net area, that means we want to look at the portions that are above and below, and it looks to me as if from -3 up to 0, I have a portion that is above the x-axis. So I'm going to call whatever that area is, we'll figure it out in a moment, let's call that A1. And that will contribute something positive to my net area. And then if I look at the interval from 0 up to 6, it looks like my function lies entirely below the x-axis. Let's call that region A2. Let me put it in red. That's going to contribute something negative to my net area. And then when I look at the interval from 6 to 8, where the overall interval ends, now my function is again above the x-axis. Maybe I'll call that A3. So that is going to contribute something positive to my net area. So the net area should be A1 minus A2 plus A3. And let's see, can we figure out each of those areas? Well, luckily they're all shapes that are straight out of a geometry textbook. So if I want to know what A1 is, it's a semicircle, I'm told that, so it isn't just any curve. And if I want to know what that equals, well, it's the area of half of a circle. Of course, we know the formula for the area of a circle is pi r squared, or you can look it up if you've forgotten it. So we have to know what the radius of this circle is. Let's see if we can compute that radius. I can see that the diameter is 3 units long, so the radius must be half of that, 1.5, or you could write r is equal to 3/2 units long. So now I just go ahead and plug into my area formula, but keep in mind that this is only half of a circle, so the area of a half circle, a semicircle, is actually going to be half of the area of the whole circle, so it will be 1/2 pi r squared. So the area of my semicircle should be 1/2 times pi times r squared, and r we decided is 3/2, and I want to square that. So that's the area A1. Now I'm going to subtract off the area A2. Well, to figure out this area, there are a couple of ways of going about it. One way is to notice that this is a trapezoid because this x-axis is parallel to the bottom of the trapezoid. So that would be one way to do it. Or if you have trouble doing it that way and you've forgotten what the formula is for the area of a trapezoid, you could break this up into a couple of triangles. Here's a triangle and here's a triangle. And then you have a rectangle in the center. So that would be another way to do it. So if you've forgotten the formula for the area of a trapezoid, I like to memorize as few formulas as possible. So maybe I don't know that. Well, I have a right triangle that's sitting right here, and I know the formula for the area of a right triangle. It's just 1/2 the base, which is 2 units long, times the height, which I can see is also 2 units. So the area of this little red triangle here would be 1/2 times 2 times 2. That's 1/2 times 4. That would be 2. So I'm going to put a 2 in here for that first little section. And the area of this rectangle is a little easier. Looks like it has a base of 2 and a height of 2. So the area of this rectangle right here would be 2 times 2, base times height. So that would be an area of 4 units, 4 square units. And then the area of this last little triangle here is exactly the same as the area of this one. It's another right triangle that has a base of 2 and a height of 2. So its area will also be 1/2 times 2 times 2, or 2. So here's the area of my circle. That's the stuff that's above the x-axis. Here's the area of my trapezoid. That's the stuff that's below. And then I still have this other little area A3 that is again above the x-axis. And it looks like if I compute its area, it again is a right triangle that has a base of 2 and a height of 2. So that would again be 1/2 the base times the height. And that would again give me an area of 2 units. And since it lies above the x-axis, it contributes something positive to the overall value of my definite integral. So all we're doing is using area formulas from back in geometry, and the value, the exact value of this definite integral should be this net area, the difference of areas. So it's the area of the semicircle that's on top, minus the area of the trapezoid that's on the bottom, plus the area of this little right triangle that is on top of the x-axis. And you can go ahead and compute all of this. Let's see, this would be 9 pi over 2 times 2 squared would be 8, minus, I guess that would add up to 8, plus 2. So what does that give me? 9 pi over 8 minus 6. And if I want to write it as a single fraction, it would be 9 pi minus 48, getting a common denominator of 8, all divided by 8. That's the exact area. And I think I threw that into a calculator, and I got an approximate value of negative 2.47. So whatever units we're working in, say we're working in units of centimeters, something like that, the net area is minus 2.47 square centimeters. That looks a little weird. We end up with a negative answer for our definite integral. Why does the answer come out to be negative overall? Well, it's just that there's more area below the x-axis on this interval from -3 to 8 than there is above. So this stuff that's below subtracts out more area than the stuff that is above adds, and our net area ends up being something negative. So if you come out with a negative answer for a definite integral, that means either you've made an error or your function is partly above and partly below the x-axis, and more of the area must have been below than was above on the interval you're integrating over. Okay, I want you to think about the next example, And this is an integral, it's the integral from negative pi to pi of sine x dx, that you certainly could do by finding an antiderivative. Unlike this one that we did up here, where I didn't give you the equation for the function f of x, and so you had no way to find the antiderivative. But instead, what I'd like you to do is use these same instructions and think about this problem geometrically. And so as a hint, what I'd like you to do is to first graph f of x equals sine x. And it will help you get to your answer much more quickly than if you find the antiderivative, evaluate it at b, and subtract the value at a, but it should give you exactly the same answer. Give that a try and then restart the video when you're ready. Okay, so I gave you this hint that instead of finding the antiderivative and plugging the limits in, you could try to think about the graph of sine x. And so let's go ahead and graph sine x. Let's see, I know it starts out at 0, 0, and at pi over 2 it reaches its maximum value of 1, and then it comes back down to the x-axis, and sine of pi is equal to 0, and it continues waving on after that. If I go to the left of x equals 0, well, I know that it reaches a minimum at minus pi over 2 of negative 1, and then it returns to the x-axis at minus pi. Sine of minus pi is again equal to 0, and then the curve just continues periodically to wave every 2 pi units. Well, if I think about the value of this definite integral in graphical or geometric terms, remember that whatever this definite integral is, graphically it represents a net area. And in particular, it represents whatever area is above, I'll say area above the x-axis, minus whatever area is below the x-axis on the particular interval from minus pi to pi that we are thinking about. Well, let's consider the area that's above the x-axis. I can see from 0 to pi that sine x is above or on the x-axis. So this area that's above is going to be this green area. And the area that's below, well, from minus pi to 0, I can see that sine x is below or on the x-axis, and so we get this red area, that's what's going to be below. But there's a symmetry going on. Sine of x is actually symmetric about the origin. It's what's called an odd function. And what do you notice about the green area and the red area? It's clear from the symmetry of the sine graph that the green area is exactly equal to the red area. So really what we have here is a, whatever this green area is, minus a. Because I can see that this red area, the region is exactly the same, and so its area will be exactly the same. And what should the answer to our problem be then? A minus a is just 0. So if there's exactly as much area above as below, be sure that your regions really are regions that have exactly the same area. Then those areas cancel out and we actually get a net area of 0. And so the value of this definite integral is just 0. Okay, well let's go ahead and look at the last page in this section. Well, on this last page, I asked you to do a definite integral. I asked you to do the integral from 1 to 5 of 2x minus 4 dx. But then as a second part of the problem, I asked you to verify it by considering this definite integral geometrically as some sort of difference of areas. So I'd like you to pause the video and figure out what the definite integral from 1 to 5 of 2x minus 4 dx is first by just going ahead and finding the antiderivative. This is a function that we are given the equation of and that we can find the antiderivative of. So just plow ahead and do that definite integral. But when you're done with that, try to think about the picture that would go along with this function, y equals 2x minus 4, and try to verify the answer that you got up here by thinking of it as a net area. And I think once you graph this thing, you'll be able to see exactly what I mean when I say consider it as a net area and verify your above answer. If you get stuck, just restart the video and we will go through it together. Okay, well, let's start this problem by just doing the definite integral. We now know that we don't care whether this function 2x minus 4 is above or below the x-axis on the interval we're talking about, in this case from 1 to 5. So we don't really care where it is. We can still compute the definite integral. It's just that if it's partly below the x-axis, that will mean we have a net area instead of an overall positive area. So we just go ahead and do the antiderivatives. Well, let's see. If I take the antiderivative of 2x, take the integral of 2x, I would get x squared. And when I integrate 4, I will get 4x. So that is an antiderivative, and I want to evaluate that from 1 to 5. Okay, that looks fine. So I'm going to go ahead and plug in my upper limit first. My upper limit is 5, so I'm going to do 5 squared minus 4 times 5. And then I plug in my lower limit, 1 squared minus 4 times 1. That looks fine. So 25 minus 20, that would be 5, minus 1 minus 4 would be negative 3. So it looks like I get an answer of 8. So what does that number 8 represent graphically or geometrically? Well, we can answer that by going ahead and doing this second part of the problem where I asked you to verify the answer by considering it as a net area. Well, it's the net area of what? This is our function right here. This is our little f of x. So we want to graph f of x equals 2x minus 4, or for graphing purposes I like to think of it as y equals 2x minus 4. And what does the graph of this look like? It's linear in x, so my graph is going to be a straight line. It will have a y-intercept of negative 4, so it has a y-intercept down here of negative 4 and a slope of 2, or 2 over 1. So I'm going to go up 2 and over 1, and up 2 and over 1. So let me try to use a ruler to make this a little bit more accurate. It should look roughly like this. And this is kind of a rough graph because I have these sort of big fat pens that I am working with. But it looks something like this. So that's the graph of y equal 2x minus 4. We are integrating from 1 up to 5. So from 1 to 5. And let me just draw some lines in there for us. I'm going from 1 up to an x value of 5. And I can see that on this interval from 1 to 5, the function is partly below the x-axis and partly above. It crosses right here at 2. So this number 8 definitely will be a net area. And let's see if we can determine what that net area is. Well, it's going to be the area of the portion that's above the x-axis minus the area of the portion that is below the x-axis. I can see from 1 to 2 that I'm going to have a triangular area that is below the x-axis, and that from 2 to 5 I'm going to have another triangular shaped region that lies above the x-axis. So whatever this area turns out to be, maybe I'll call that A2 and this area A1. A1 contributes something negative to my net area. Maybe I'll just write it this way as minus A1. And A2 is above, so it contributes something positive to my net area. And now all I have to do is see if I can figure out what those areas are. Well, luckily, this function was a straight line, so this is a true triangle here. And in fact, it's a right triangle. So if I want to know what this area is, I just do 1/2 its base, its base is 1 unit long times its height, which appears to be 2 units long. So it looks like that area would come out to be 1. So I want minus that positive area. So I will have a minus 1 in my net area. And A2 is also a triangle. That makes it very convenient. And so if I want area A2, it's 1/2 its base. Well, how long is its base? It goes from 2 to 5. 5 minus 2 would be 3. So it has a base of 3. And the height here might be a little hard to tell from my graph, but I could plug 5 into my function to see what the output value is. And if I plug 5 into this function, 2 times 5 minus 4 would be 10 minus 4 would be 6. So the output value here is 6 if my graph isn't perfect enough to tell. So the height of this thing is 6 units. And so my area will be 1/2, the base is 3, and the height is 6. So it looks like I would get an area of 18 over 2, that'd be 9. So I'm going to say plus 9 because this area, this region, lies above the x-axis. So minus the area below plus the area that's above, and you notice -1 plus 9 does give me 8. And so I verified my answer up here by considering my region as a net area and using old-time formulas from geometry to find each of those areas. So that's kind of nice. At least it makes us feel that our interpretation for this definite integral is correct, at least in this particular example. I definitely got something that I could verify using geometry formulas, and the number that I got for the definite integral matched this idea of the net area. Area below is negative, area above adds something positive to the overall net area and to the overall value of that definite integral. Okay, well, let's look at one more example. This says compute and then interpret. So let's see if we can do that. So we just want to go ahead and compute this definite integral. That is our first job, and then we'll worry about interpreting it as some kind of area or net area. The curve, by the way, is y equal x cubed minus 4x, and I've actually graphed that roughly over here for us. Okay, well, let's just do the definite integral, then we'll worry about interpreting it later. So if I want to do the definite integral, I just go ahead and integrate this term by term. So integral of x cubed, that would be 1/4 x to the 4th, minus the factor of 4 gets carried along. There's really x to the 1st, so I would have an x squared with a 1/2 out in front, and that's my antiderivative. That's what I'm going to want to evaluate from -1 to +2. Okay, well, let's go ahead and just simplify this a little bit more. This would be 1/4 x to the 4th minus 2x squared, evaluated from -1 to 2. So let me go ahead and plug in these limits. I'll plug in the upper limit. Let's see, that would be 1/4 times 2 to the 4/16, that'd be 4, minus 2 times 2 squared would be 8. So that's the antiderivative evaluated at 2. Now I'm going to subtract the value at -1. When I plug -1 in, I have 1/4 times -1 to the 4th, that's just a 4th, minus 2 times -1 squared would be a -2. And now let me just go ahead and simplify it. Just ignore this writing right here. That's just my slide number. And I'm going to move this up a little bit because I'm running out of room. So I'm going to go down to here. So let's see. I have a -4 in my first parentheses minus a 4th minus 2. That'd be 4th minus 8/4. That would be a -7/4. So it looks like I end up with -4 plus 7/4. Well, what's that equal to? That would be equal to -16/4 plus 7/4 is -9/4. Now I'm getting a negative value for my definite integral. So even before I consider my graph and the areas, remember that this does represent a net area. What's that going to tell you about the areas when I draw my graph over here? Well, it means for this particular function, y equal x cubed minus 4x, there must have been more area below the x-axis than there was above the x-axis on this interval from -1 to 2. So I'm starting here at -1 and I'm ending here at 2. Well, let's see if that's correct, or at least looks correct from the picture. And so if I draw a vertical line here at -1, I can see the function is above the x-axis until I get to 0, and so all of this should contribute something that is positive. So if I call that a 1, that will contribute something positive to the net area. And then from 0 up to 2, the function is below the x-axis, so that will contribute something that is negative to my net area. So I would have whatever the positive green area is, and then minus this red area. It would be A1 minus A2. And does it look correct that we come out with a negative answer? Well, I believe it does. This function is an odd function. It's actually symmetric about the origin, and so this sort of loop of the graph has just as much area in it as this one does from -2 all the way to 0. But you notice that we're only taking half of this hump of the graph. We're only doing the area of half of that. So there's clearly more area below the x-axis than there is above the x-axis on that interval from -1 to 2. So the negative answer makes sense. So now we know that we can find the definite integral of any function that's continuous on its interval from its lower limit to its upper limit. It doesn't matter whether the function is always above or on the x-axis, or whether it is always below the x-axis or partly above and partly below on the interval we're looking at. We can always find the indefinite integral of this, provided we know how to find the antiderivative of our little f of x. The only thing we have to remember is that when we get an answer, we have to know how to interpret that. And the only time it will represent the area under the curve is if our function is completely above or on the x-axis. If it's partly above and partly below, we will actually end up with a number that we must interpret as the net area. And that does it for this section on the fundamental theorem of calculus. And just keep in mind that if you are interested in a rigorous proof of the fundamental theorem of calculus, we just did that intuitive kind of picture proof, which is really more of an argument. The rigorous proof is included at the end of this section, either in your handout or in your booklet. So I encourage you to read through the rigorous proof of the fundamental theorem of calculus, as it is one of the most important theorems that you will meet in all of calculus.